Hello and welcome to a new video in a course on calculus. In the previous videos, we defined infinite series and we gave some tools for checking whether a series is convergent or divergent. So in this video, we'll continue to give more tools, and our new tool is the root test. So previously we've talked about the nth term test, the comparison test, the limit comparison test. We also talked about the ratio test. So in the previous video, we made a distinction between the comparison tests and the root test. So we said that the comparison tests, we have a sequence an we have a sequence an and we're summing that. So we have this series and we're interested in the question of whether this is a convergent series or not. And the way we did that is by comparing it. So this is analyzed by comparing it to another series. So we compared it to another series, and based on whether or not you have an inequality between these two, we used the comparison test. And if we had if we looked at the ratio and we had some we had the limit that is finite and not zero, we could apply the limit comparison test. So I'm gonna let you go. I'm gonna let you go and check these videos or check your notes regarding these if you already watched the videos. Now we made the distinction that the ratio test doesn't require trying to figure out what series to compare your given series with, because it just deals with the series itself. So you have a series, the sum of an from n equals 1 to infinity, and what the ratio test, questioned was this, the limit of this thingy. So it looked at the ratio of these things, of these coefficients, and we considered the limit, and we said that there are three cases. So the first one was that if the limit is less than 1, then we have convergence. If the limit is bigger than 1, we have divergence, while if the limit is equal to 1, it was inconclusive. So this is what we had last time. Now the root test is more of it's more similar to the ratio test than to the comparison test, because we don't compare the series with other series or the sequence summand to the other summand. What we do is that we just consider the series itself. Let's say we have the sum of an from n equals 1 to infinity, and we ask now what's the limit of the nth root of the summand that we're talking about here, which is an. So I remind you, the nth root of an, so it's the absolute value of an, and you're taking the nth root, which means you're raising to the power 1 over n. Now, I remind you, when using the ratio test, there was something that suggested that one should apply the ratio test. So, for example, when we solved in the last video, when we solved the fact that this is a convergent series, so we mentioned that n factorial, n plus 1 factorial is actually n plus 1 times n factorial. And we said that this connection between the coefficients an plus 1 and an made it this connection between the coefficients an plus 1 and an suggested that the ratio test, because we're considering the ratio of these two, might be a good thing to try to use, right? So this was suggested, like the use of the ratio test suggested itself. So similarly here, the root test is gonna say, you need to compute this limit, right? You need to take the sequence that you have, the an, take the absolute value of it and take it to the power 1 over n. And then you ask if this limit, if this limit is less than 1, then we say that, then we have that the series is convergent. If the limit is bigger than 1, then the series is divergent. However, if the limit is 1, then the test is also inconclusive, just as in this case. So it doesn't tell us anything. Now again, the use of the root test is gonna suggest itself. Like, in what sense? Well, in the sense that if you have a summand, if you have a series where the summand contains some power of n, like it's let's say n to the n or something like that, so it's kind of like the root test is suggesting itself because you want to get rid of an ugly power of n. The way to do that is to take the nth root of it, okay? So let us take an example to just clarify this theorem and make it clearer. So let's take the example, let's say we're asked the question, is the sum of n to the n over, let's say, 4 to the 2n, I don't know, from n equals 1 to infinity, is this convergent? Well, if you look at this, this series, it looks like it's very much not convergent, because n to the n grows very badly, while this still grows, like it still grows exponentially, still grows fast. However, it can't beat, like it can't beat n to the n. So with that said, like you have powers of n, like you have n to the power n, and you have 4 to the power 2n, so there's an n in the power. So it's kind of suggesting itself that the root test might be a good thing to try here. So let us try it, I guess. So let us try to take so the sequence an is this thing. So an is n to the n over 4 to the 2n, excuse me. Now an is positive, so no need to carry the absolute value. Let us look at the nth root of an. Now the nth root of an, it's an to the 1 over n, and this is equal to n to the n over 4 to the 2n, all of it to the power 1 over n, right? And thus this whole thing is equal to, if you distribute this to this and that, the n over n will give you 1, will cancel out, and you'll be left with n in the numerator, because it's going to be n to the power 1, over 4 squared, because the n's will cancel. So so this is what you're left with, and the next thing to do is to compute the limit of that thing. So we're going to compute the limit of this thing, and you will get that this is the limit of n over 4 squared as n goes to infinity. But what is that thing? Well, it is just infinity, and this is plus infinity. So but this thing is clearly strictly bigger than 1, plus the series is divergent. So so this thing is a no, it's divergent actually. So the sum of an is divergent. And it might be nice to mention every time what test you're using. So this is by the root test. Okay. So this is what we have. So let us take another example just to make things more clearer. So the next example we're gonna do is this thing. So we already know that the sum of 1 over 2 to the n from n equals 0 to infinity, this is finite, or this converges because it's a geometric series with r equals to half, which is strictly less than 1. So I remind you, geometric series, it takes the form ar to the n as n goes from 0 to infinity. So this is what we have. So we do know that this is a convergent series. Now the question is, what happens if we raise the summand to the power n? If we take this and raise it to the power n, well, in that case, you see, there's something that is suggesting itself. Well, we have a power n, right? So it's suggesting itself that we'd better use the root test to get rid of that ugly power n, right? So if we use the root test, like if you take the nth root of the absolute value of an, and this is an in this case, this thing is an, and if you take the nth root of it, which means if you raise to the power 1 over n, well this n will go away and you'll be left with this thing, right? You'll be left with 1 over 2 to the n, right? Now this 1 over 2 to the n, we're interested in the limit of it to apply the root test. So let us compute the limit, but clearly the limit of it is just 1 over infinity, quote unquote 1 over infinity, and thus it's just 0, right? So the limit of the nth term, the nth root of the coefficients is 0, and 0 is strictly less than 1. But if you go back to the test, you see that if the limit is strictly less than 1, then the series is convergent. So we just got that the series is convergent by the root test because the limit is less than 1. So you see, it's kind of coming for free that if so you can prove something more general here. So maybe here's an interesting fact, I would say. So here's an interesting fact for you. If you have that the sum of n equals 1 to infinity is convergent, then the sum from an from n equals 1 to infinity to the power n is convergent. And this is nice and easy. Like if you take any convergent series, right, and you raise the coefficients of it, if you raise the things you're summing, the summand to the power n, then you still get a convergent series, right? So this is very interesting. So let us prove this. So let me show you why this is true. Well, if you look at this series and you're interested in proving that, in showing that it's convergent, and you have a power n here, so it might be interesting or it might be useful to apply the root test. So if we apply the root test, which says that we should consider the limit as n goes to infinity of the nth root of the absolute value of an. Now let's suppose here that an is just is just positive for simplicity. So let us say here, though it works in general cases. This is gonna be the limit as n tends to infinity. And excuse me here, we're applying the root test not to this series but to this series, which means our summand is this whole thing. So there's a power n here that I missed. Okay. So this is a n to the n, and the whole thing is raised to the power 1 over n. Now the n and 1 over n cancels out, and this is the limit of an, because an is positive as n goes to infinity. So we can get rid of the absolute value, though it doesn't matter. So I claim that this limit is 0, and thus this is less than 1, and thus this series is convergent by the root test. But why is this limit 0? Well, that's an easy consequence of the nth term test. So recall, by the nth term test, since the sum of an from n equals 1 to infinity is convergent, then the limit of an as n tends to infinity is 0. So this thing we know for sure. Whenever we have a convergent series, the summand of it must go to 0 as n goes to infinity. So this thing we know from the nth term test. And thus, since this limit is 0, then which is strictly less than 1, then by the root test, the series is convergent. Which series? Well, it's the series that we applied the root test to, which means it's this series because we took these coefficients. So so we just got that this is true by root test. Okay, so this is what we have, and this is very interesting to keep in mind because you see it kind of uses the nth term test and the root test in the same place, but it's just a kind of interesting fact to keep in mind, not a big deal.